Now let's just look at this RB. What is it? Is equal to U naught minus U by U into R naught. Naught minus U by U into R naught. So let us actually write this as R naught into U naught by U minus 1, and pull out. Let's pull out R naught. Let's pull out U naught. So we'll get 1 by U minus 1 by U naught. Correct. And now let's substitute for 1 by U from the earlier equation. I had written here something. Right? If you go back here, I had written this. So we can actually use that. So by the Lenz's law, right? If you look at 1 by U, that is 1 by F minus 1 by D, right? Minus 1 by U naught. So minus 1 by U naught is plus omega 1 by omega plus 1 by omega D minus 1 by F, right? And therefore, oops. Why is this nice? And therefore, RB is equal to R naught U naught. So 1 by F will cancel off and we'll get 1 by omega D minus 1 by D. Okay, and it actually makes sense. So what this means is that if your D, that is, if the point is such that D is equal to omega D, then RB equal to 0, right? If D equals omega D, then there is no blur. Then there is, then the point appears in focus. Or in other words, there is no blurring. Then the point means the scene point, okay, will appear in focus, else not. Then this RB is, right, you don't have to worry about RB being sort of, right, I mean a negative number, right? That can also be negative, but the interpretation is that it's not like RB is negative now. It just means that whether this blur circle, so in this diagram, right, whether this point of focus, whether it is in the front of the image plane or on the back. Okay, if it is negative, it means that the point of focus is at the back. Okay, so in that sense, we won't really worry about the sign of RB. For us, all that matters is the fact that if you are not keeping an object at this WD, which is the working distance for that lens, then, right, it will come blurred. So what this then means is that, right, imagine if you had really a 3D scene, right? And now if I had a lens, right, which is trying to image it, and then I have an image plane. Now clearly, right, I know it is impossible for me to satisfy Lenz's law for all the points, because the Lenz's law will only say that, for this focal length and for this whatever, right, this aperture and all of that, aperture radius, that should be omega D. Now maybe, right, one of these points is actually satisfying let's say a point here is actually satisfying the Lenz's law. So that will come in focus. But then the other guy is not at omega D, right? Something is in the front, something is closer, something is farther, and each one of them will start to introduce its own circle of blur, and whose radius will also start to change now, right? Because they are all not at the same sort of, right, a distance. Now because of this, right, what happens is sometimes, right, people say that that this notion of linearity and shift invariance, especially the shift invariance part, right? Sometimes you see some papers saying that a lens is not shift invariant. Okay, but that is a kind of a subtle point. It's actually not true. Okay, what is true is that a lens is actually shift invariant. Okay, it is a linear and shift invariant system, but it becomes more tricky as opposed to a 1D case, because you have to understand what does it mean to actually analyze a system for say shift invariance. Okay, now the point, right, at this point of time, at least you should be able to digest the fact that why is it that you see images being formed in lens the way they are formed. Some things are in focus, some things are out of focus, right? This is happening because of this, right? It's impossible to bring, right, everything into focus, but there is an associated notion of depth of focus, right? So there is a notion of depth of focus, or depth of field. In fact, it's a more common name. So this depth of field changes for every lens, okay, depending upon its aperture size, depending upon its focal length, depending upon this circle of confusion that you admit, because it also depends on what you admit as being in focus. Okay, so So there are 3 or 4 things, right, on which the depth of field is a function. Now you can have lenses for whom the depth. So what this actually means is that, what is the range of depth, right? That means what is the, so for example, right, if 2 points are away by a certain sort of, right, a distance from the lens, will you already start to see blur, or they can go this much farther off, and then maybe, right, you will start to see that, right, these two are not do not have the same level of blur. Or is it that even if they are just microns away, your lens can still trap the fact that, right, that this cannot be brought into focus, or they both cannot be simultaneously in focus, right? So this depends on the lens. So for example, a microscopic lens, in which if you just keep 2 layers, if you show which are just microns away, it can still kind of find the fact that they are not at the same depth, simply because this aperture, this lens will reveal it. Because when you see the image, it will look like this guy is in focus and this guy is blurred, or if you are focusing on this guy, this way it will turn blurred. Okay. Whereas you may have lenses for which, right, you can go meters apart and still be able to see, right, all in focus. And then there could be situations where let's say something which is really far, where there is a big depth difference, and then you see a difference in blur. Okay, so this depth of field, so it is not true that all lenses will have the same depth of field. So what we are saying is, it depends upon each lens. But the image formation process is still fundamental. That is all this only. But but then whether you see this blurring effect or not, at what kind of depth differences do you see an appreciable change in blur? It depends upon the depth of field of each lens. Now this could be used here, like I said yesterday, it could be a nuisance, or it could make, right, new sense for you. So right, so so some people actually realize the fact that if you are seeing a difference in blur, that means what? That means that the lens is telling you that, look, this world is not plain. It's actually a 3D world. What you are looking at, it's giving you that information. Right? What you want to do with it is your outlook. Is it not? See, when I'm capturing an image, and suppose I see that this image has got a different blur there, a different blur here, then I should actually wake up my senses and tell me that, oh, the lens is actually telling me that the world is 3D, the one that you're looking at. If I see that, right, all of it is in focus, then either I can conclude that this depth of field is probably very large. That is why, irrespective of where the objects are, everything is coming in focus. But if I know the depth of field for that lens, and I still see that, right, everything is coming in focus, then it means that probably the scene is a planar scene, right? Which is why I can bring all points into focus. Because right, imagine instead of a 3D world, if I had just a planar scene like that, again fronto-parallel, every point is at the same depth d. So either all of them are blurred by the same amount, because they will all have the same blur radius, right? So they are all blurred by the same amount. Or I can move this. Well, if I can't move the lens, then maybe if I have a way to adjust my focal length or my u0, then I can always bring them into focus, bring the entire scene into focus, right? But in general, it's not true, okay? Because the scene, you need not be constrained to be a plane. It could be inclined, in which case again you will see a different kind of blur, because then your depth will start to change, right, for each point. Or if the scene is completely a full-blown 3D, again the same thing, right? You will get an image that will start to. So a nature of blur like that is called a space variant blur. Okay, a 3D scene introduces what is called a space variant blur. Okay, and if you have a planar scene that is fronto-parallel, you can. It is possible to arrive at what is called, well, why is it possible? You will get. It is possible to bring the scene into focus, but you will definitely get space invariant blur. Okay, we call it a blur because it's like something not being in focus, right? It's spreading. Okay, now, so because of the fact that, right, this introduces a space variant blur and all, right, people generally hurriedly conclude that the lens is space variant. Because the scene is 3D, then see, you have a space variant blur, and therefore, right, it's a space variant system and all. Okay, that is not correct. Okay, now we want to understand that. I can simply say that assume the lens is shift invariant and move on, but I generally don't do that. Okay, because I think when we want to understand image formation, it's always good to, because when you understand this, then somebody talks about a coded aperture, anything else, and somebody talks to you, you will at least be able to appreciate what's going on. Okay, now let's kind of look at this notion of linearity first. Okay, now when you talk about linearity, right, what do you actually mean? You are kind of thinking, right, in your mind that if I input an image I of xy, okay, now for the time being I'll simply take sort of a continuous case. It doesn't matter. Okay, it is a discrete or continuous. Let's say continuous. I of xy, let us say, gives you, let's say this imaging system gives you g of xy. Then by linearity means what? It should satisfy the superposition principle. That means that if I do alpha times I of xy, it should give me alpha times g of xy. Correct? Actually, alpha can be real, alpha can be complex, right? In general, when you talk about superposition, alpha can be any constant, real or actually imaginary. But anyway, let's not worry about imaginary constants. So you're looking at image. Then I1. Okay, now if I1 of xy produces g1 of xy, I2 of xy produces g2 of xy, then I1 plus I2, okay, all that xy and all is still there, should produce g1 plus g2, right? So one of them is called actually homogeneity, right? As you all know, this is called the homogeneity property. The other is called additivity, right? This is what we call as additivity. So when these two together, when they are satisfied, then we say that superposition holds. Right? Then we say superposition holds, and which means that you have actually a linear system. Now the slight complexity, right, that arises here is, what do we mean by an input image? Okay, right, that's the way we interpret. No, when you have an linear system, what do? You apply an input to watch for the output. That's the way we interpret, right? Now when I write here I of xy, it's not even clear to me what is that input image that I'm trying to talk about, right? So what is this guy first? Output probably is clear. What I can get out of the lens. So what is this now? Okay. So the way we interpret this I of xy is that this is the pinhole focused equivalent. Okay, so it's like saying that if I gave an image that is completely in focus, how does this lens? So it's like saying that if the lens was not there, I would have seen. Actually, right, like I told you, right, I'm introducing the lens, right? Without the lens, what do I see? I see like, a pinhole through which my rays are coming, and then the only problem is my intensity, right? Let's just assume that some calibration problem. Okay, let's just assume that if there was an aperture, only a pinhole, then I would have seen a focused image. Okay, except that I said it might be dark, but let's assume that I can expose it long enough so that I get an intensity that would be the same as basically whatever I could gather through a lens in terms of accumulating all the rays and so on. Okay, so these two, let's just assume that we are able to do that. Then when you introduce a lens, something is going to happen to this I of xy. Correct? It's going to change. And now we want to understand. So it's like saying that I have a point light source. Okay, because this let's start with actually a point light source, because then we can have one point light source, add one more point light source, then place both of them together, right? That's a way to argue. So when you have one point light source, right, with respect to which, okay, you see a focus point, and then the point is, right, when you introduce an image, introduce a lens, okay, something will change. Okay, now we tend to interpret this as a complete image, which is also okay, which means that not just one kind of one sort of point light. So there's a whole sort of thing, a collection of point light sources for which you get an I of xy, and then if you replace the aperture replace the pinhole with a lens, it turns into some g of xy. And now you are asking, if I increase my intensity, will my output image that I get out of the lens, will that also correspondingly increase? If I have two such scenes or two such points, right, you can think of this is easier understood if you try to think of it as a point light source. One point light source leading to one image, another leading to another image. Can I keep them simultaneously? Will I get a summation of what I got when they were kept individually? Right? That's the way we look at it. And clearly, the linearity part is very straightforward. And one of the key things, right, that you have to remember is the blur circle let me write that here. So one of the key things is that it's this central ray. Okay, that is where we kind of, when I told you that we borrow from the pinhole, right? The analogies. One analogy that we have already borrowed is this: the pinhole focused equivalent. So the pinhole, it still has a role. Okay, it is not like, it has no bearing once you introduce a lens. When you think of a focused image in a lens, we can correspondingly think about, oh, that is what I would have obtained if I had really a pinhole camera. So what the lens is yielding is really a pinhole output. Okay, so that way there is still a relation between an analogy between what is going on with a lens and what you get with respect to pinhole. The other thing, right, that you have to capture is the fact that this guy, this central ray, which goes undeviated, this undeviated central ray obeys. What do you think it obeys? The perspective projection model. See, for example, right? If you think of where kind of, right, this is hitting the image plane, and where this is, right? This angle is equal to this, and whatever we did with respect to pinhole, right? That kind of a PP model, a perspective, this one, a projection. This guy obeys, okay, because it goes totally undeviated. And the third interesting point is the blur circle gets formed about this guy. So it's like saying that, so the principal ray or the central ray about which your circle gets formed, right? And note that obeys because and the blur circle is formed around it. Okay, around it, in the sense that after it hits the image plane, right? So the blur circle is getting formed around it. Now, the point is, right, so something which is kind of, which we will again go back, right, in terms of a pinhole. Now okay, now all right. I mean, right, prior to going to the shifting variance, right, I haven't even talked about linearity. I'm not finished with linearity yet. So as you can see, right, the linearity principle. Suppose you assume that I have actually a point light source. Okay, let me assume that I have one point light source, right? A point light source. Okay, we go back here. I have a lens. I have an image plane, and let's say, right, that this point light source, when it goes, kind of blurs something, and then what I see is that. Okay, what I see is this kind of a blur circle, and of course, right, you have a central ray that is still sitting there, okay, about which this whole thing is getting formed. Okay, there is a central ray about which the circle is getting formed. Now, what do you see? One of the things is a lens by itself, right? A lens is something which neither adds nor removes light energy. Adds nor removes light energy. Right? Because whatever enters, it will completely focus them, or it will spread them into a circular confusion, and it by itself does not hold anything back. Whatever is coming in, it's just kind of throwing it all out. And because of this, what you can imagine is that if instead of a lens, if you had a pinhole, and suppose you saw some intensity there, that would have been a point in focus. No, it would have had some intensity. Correct. Now, when you replace that aperture with a lens, now what has happened? Now that point has gotten spread now. But because of the fact that the lens itself hasn't added or done anything, what do you expect? To sum up all the intensities within this blur circle, that should be the same as what you see as a focus point, right? Because you can't lose energy anywhere, no? Correct. Either the lens is also bringing it into focus, in which case you won't see any change in the intensity. You saw a point earlier, you are still seeing a point. They both will have the same intensity. Correct. Now, if blurring happens, then it means that the intensities are getting spread now, which means that the intensities may be lower, because as you walk around, you may not get the same original intensity that you got for the focus point. But if you sum up all the intensities that are lying within this blur circle, they should all add up to the same focus point. This is fine, right? Okay, there isn't anything unusual about that. So what this means is that if I of xy, if this is a point, right, a point light source, if this gives you g of xy, which could be blurred, then double integral g of xy dx dy should be equal to I of xy. Correct? This is if you had a point light source. I'm not trying to write out a convolution model. I'm just saying that if there was a point light source, if it spreads, then because the lens is not going to take off anything, so you just add up all the intensities within the blurred circle. It will add up to what you saw as a focus point. Now, imagine that I actually increase my intensity here, my radiance of that point, and corresponding to that, let's say the kind of pinhole focused image went up by alpha. Correct? In the scene, I somehow, right, I make this point light source brighter or whatever, dimmer, and correspondingly, what happened? My point, the pinhole point, the focus point, will also either go up or go down by some alpha. Now, again, if you introduce a lens, what will happen? That intensity will spread, and it is again true that you will get alpha g of xy, because if you integrate this, it should give you alpha I of xy, right? It cannot, it follows. Now, instead of one light source, suppose let's say I1 of xy gave you one blur circle, which is let's say G1 of xy. And then I introduce another point light source somewhere there. Okay, this could be a 3D world. We don't care now. I'm not assuming planar at all. Some other point lies somewhere here. So this point was here. This point is here. And then for that point light source, I get I2 of xy is the intensity that you get if only that was present in the scene. Corresponding to that, you have what is called G2 of xy, correct? And now, if you say that I apply both of them together, right? So at one time we are applying only one at a time, and suppose I put them both together, okay, then you will get what is called G1 of xy plus G2 of xy. Correct? I mean, that's what you'll see. You'll see one blurred circle, then maybe something else, which could be overlapping, need not be overlapping, but as far as the whole image plane is concerned, if I add up all the intensities in the image plane, that should add up to those 2 point focus points that I had originally. This is strictly speaking, right? There you can think of situations where where kind of this can fail, okay, but those are very extreme situations. Like for example, what's called a self-occlusion. It's like saying that. I mean, how do I show that? Anyway, I mean, it's not really relevant. I mean, I don't want to take you off that track. But it's like saying that if I had an object like this, okay, something like this, right? If my 3D scene looked like that, okay, and then right, if this whole point is not there, and if I had only this, then all these rays, right, can kind of go through the lens. But then if I put this alone, then again all these rays can go through the lens. Now, if I put them both simultaneously, this guy's rays get blocked by the guy in the front. Right? I mean, see, this ray cannot reach, because there's some point sitting in front which is blocking it, right? In such cases, this will fail, but let's not worry about such cases. Okay, simple. Okay, let's just keep the math simple and just keep the principle simple. But yeah, right? I can think of situations where, in fact, if you watch through actually a keyhole, right? When you have a room and through the keyhole, if you watch, right, you will see that the image formation does not follow this, because you have what is called a partition. So the blur circle, right, itself will get truncated, because not all rays are going to come. Some are getting knocked off, right, and so on. So that is all only for explaining those strange situations. So we'll just keep it simple. Okay. So what this means is that so you all agree that a lens is linear, right? Okay. So clearly, right, lens is a linear system. Okay. I'll stop here because the next notion is one of shift invariance, and that will require some explanation. Okay.